Okay, so what we have discussed so far, the Lewis theory, okay, or the Lewis way to draw electron structures, plus the VSEPR theory, plus the valence bond theory, plus the hybridization theory. All of them are actually what make up the localized electron model. So from all of these information, you can basically determine the overall shape and bonding of molecules. One thing though that it doesn't do much justice of is lone pairs. So up until this point, we've just looked at lone pairs as basically non-bonding electrons which are loosely bound on one atom. Okay, and another thing that this localized electron model actually does not take into account will be resonance structures. So one theory which actually picks up on these flaws of the localized electron model is the molecular orbital theory. So this is basically a theory which states that electrons occupy molecular orbitals that belong to the entire molecule rather than to an individual atom. So basically, if we assume before that an H2 bond or an H2 molecule, hydrogen, is actually the result of head-on overlap of two 1s hydrogen atoms, then for the molecular orbital theory, this bond is actually as a result of a molecular orbital belonging to the entire H2 molecule. Okay, so let's look at some examples or applications of the MO theory. So, but before we do that, note that since molecular orbitals are orbitals, they can actually hold up to a maximum of 2 electrons of opposite spin. If you remember in the valence bond theory or in the localized electron model, this is just represented by m sub s, the quantum number equal to positive or minus 1/2. Okay, so the same thing can actually be said for molecular orbitals. Now, similar to atomic orbitals as well, if you square the mathematical wave function of atomic orbitals, then you get the electron probability, or well, rather the probability of finding an electron in space in a specific molecular orbital. Okay, we're not going to go into the math of the second bullet point. But what instead we want to go over with are 4 principles of MO theory. First one is pretty simple, which actually just says the number of molecular orbitals are conserved, meaning if you are combining together 2 atomic orbitals to form molecular orbitals, basically you will have formed 2 molecular orbitals as well. So again, from 2 atomic orbitals, you form 2 molecular orbitals. From 4 atomic orbitals, you form 4 molecular orbitals, and so on and so forth. So for example, let's just consider hydrogen gas or molecular hydrogen, as we have mentioned earlier. So if you mathematically add the wave functions of 1s from hydrogen and 1s of another hydrogen, then you get 2 answers. You have this sigma molecular orbital, again, just the mathematical sum, okay, which is just called a sigma molecular bonding orbital, okay? And then if you get the sum of a 1s hydrogen and the negative of a 1s of another hydrogen, basically if you subtract them, then what you will have instead is a sigma star anti-bonding molecular orbital. Okay, so according to the first principle of MO theory, you have a higher probability of finding these 2 electrons from each hydrogen in the sigma orbital rather than the sigma star orbital. And that can be further explained by the second principle of MO theory, which just says that in general, bonding orbitals are lower in energy than parent atomic orbitals. And the atomic bonding orbital or anti-bonding orbital is higher in energy than parent atomic bonding orbitals. So this is how you usually draw MO diagrams. And we start first with individual, sorry, looking for my pen. We start first with individual 1s orbitals of two hydrogens. Okay, so basically if these two 1s orbitals form a molecular orbital, then the bonding molecular orbital here, which is again sigma, and we're gonna call it sigma 1s because it comes from two 1s orbitals, two 1s atomic orbitals. Okay, it says here that since the y-axis is energy, it says here that this bonding molecular orbital is actually lower in energy, or as you may have remembered when we were discussing energies in passing detail, this is more stable than the individual atomic orbitals themselves. Now, the individual atomic orbitals of these two hydrogens are actually more stable, on the other hand, than this sigma star 1s antibonding orbital. So as you can see, this sigma star 1s antibonding orbital is actually empty. So when drawing MO orbitals, we have here one electron from A1s, one electron from A1s, and this remains empty because we have to fill up this orbital first. So that basically is the second principle. Now, the third principle is basically you have to obey also the Pauli exclusion principle and Hund's rule of maximum multiplicity to molecular orbitals, because you know they are orbitals themselves. So if you remember when we were discussing Pauli's exclusion principle, the Pauli exclusion principle just says that no two electrons can have the same set of quantum numbers. So for example, these two electrons in the sigma 1s orbital cannot be pointing both in the same direction. According to Hund's rule of maximum multiplicity, and this will actually apply later when we have p orbitals being combined to form molecular orbitals, then that just means that if you have degenerate orbitals, meaning of the same energy, you have to fill them up first in order, but make sure that when you do, you have fill all of those orbitals first and then put in electrons of opposite spins. Okay, now the third principle of MO theory also segues us into bond order. Let's say, for example, let's consider a hypothetical H2 minus bond. So this is hydrogen molecule with an extra negative charge, meaning it has gained an electron. So the bond order formula in molecular orbitals, this is different-ish to what we have discussed before in chapter 3. The bond order formula for MO diagrams or MO theory is the number of bonding electrons, meaning these, okay, minus the number of anti-bonding electrons, meaning these, okay, basically in orbitals with a star, is basically the average, okay? So the number of bonding electrons minus the number of anti-bonding electrons divided by 2. Okay, so if we don't actually have this electron, then the bond order for just hydrogen, okay, not the one with the negative charge, is actually equal to 2 minus 0 divided by 2, so it's actually 1, okay? And then the bond order for H2 minus is actually 2 minus 1 is equal to 2, and this is actually equal to 1/2. So what this just means is the higher the bond order, so the higher the bond order, the more stable the compound is. So this just says that, sure, hydrogen 2 minus actually, or molecular hydrogen with the negative charge is actually stable, but it's not, but it is half as stable as molecular hydrogen without any charge. So let's say, for example, we extend this drawings to dihelium. So dihelium, for example, here has a bond order of 2 minus 2 divided by 2, so that's 0. So bond order of 0 just means that dihelium cannot exist. And that makes sense because helium by itself is a noble gas, meaning it doesn't really want to form bonds. Okay, but for example here for dilithium, okay, we're not shown here the 1s orbitals and the sigma star 1s orbitals, but if you consider the 2s orbitals which form the sigma 2s and sigma 2s star bonds, we see that for dilithium, the bond order is 2 minus 0 over 2 is equal to 1. Okay, so that just means that the formation of dilithium, which is a metallic bond, is just more stable than the formation of dihelium. Okay, now as you move past the periodic table from lithium to beryllium all the way up to boron, in which you're actually forming or you're actually combining 2p orbitals to form pi orbitals. And again, the same principle still applies. Since for 2p orbitals, we actually have 3 orbitals per atom, okay? So if we combine them to make molecular orbitals, you will have a sigma 2p orbital, a sigma star 2p orbital, okay? And then 2 pi 2p orbitals, which are bonding, and then 2 pi 2p star orbitals, which are non-bonding. Okay, and normally this would be how the energy, normally this would be how the energy distribution would look like, meaning the 2p orbitals, the sigma 2p orbitals are the lowest in energy, followed by the pi 2p orbitals, followed by sigma 2p star, and then lastly the sigma 2p star will be the highest in energy. Okay, so for example, if you actually make diboron, this is what you expect. And magnetism actually plays a role too for other compounds, not just metals that we have discussed before. A compound is supposed to be paramagnetic if at least one paired of electrons, if you have at least one unpaired electron, sorry about that. And you have a diamagnetic compound or metal if all of the electrons are paired with each other. So from this structure, it's safe to assume or safe to look at that the 2s orbitals of the sigma 2s and sigma star 2s orbitals of diboron, all of these are valence electrons, are all paired. But diboron actually in an experiment is observed to be magnetic. So in cases of boron, and we'll name 3 more elements, so what actually happens is this PS mixing. So basically, instead of having the sigma 2p orbital lower in energy, these two actually get flipped, okay? And instead we have this order, okay? And following Fund's rule of maximum multiplicity, we have to half fill first each of these individual pi 2p orbitals. And that's why now, with the structure on the right versus the structure on the left, the structure on the right, we have 2 unpaired electrons, and that's the reason actually why the bonding order here, or sorry, why diboron is actually paramagnetic instead of diamagnetic. Okay, here's just another way to look at it, but there are actually these 3 which have these odd cases. Okay, again, instead of these or this sigma 2p orbitals being lower in energy, they're actually higher in energy than the pi 2p orbitals. Okay, one thing to remember them will be this is B, C, N, so that's actually Bacon. Okay, but of course not including the Oh, because that's oxygen. So bacon. Okay. Um, and as for the case of the others, let's say for example, if you have oxygen and fluorine, they do not undergo FPS mixing. So for oxygen and fluorine, sigma 2p is still the lower energy than pi 2p. Okay. So you can also calculate the bond order here for diboron. You have right now two electrons which are bonding there, also two bonding electrons there. So that's going to be 4, and then these are non-bonding, so 4 minus 2 divided by 2, that's actually going to give you a bond order of 1. Okay, the same thing here for carbon, except that now you have more bonding electrons. This is 6 minus 2 divided by 2 is equal to 2, and then the same thing will apply. So notice that diboron is paramagnetic. Dicarbon and dinitrogen are diamagnetic. Okay, oxygen is actually paramagnetic. Okay, and again, let's just calculate here the bond order for oxygen. Oops, sorry. The bond order here for oxygen is how many bonding electrons do we have? 2, 4, 6, 8. Okay, so that's 8 bonding electrons. Minus how many non-bonding do we have? 2 and 4. So it's going to be 4 divided by 2 is equal to 2. Okay, and then fluorine, which is diamagnetic, has a bond order of 1. Alright, so again, keep track of those of these two, how they are different from boron, carbon, and nitrogen, the Vacant series. Now, a few things that I'd like to define here. First, this empty orbital in fluorine, which is also this empty orbital in fluorine is called the LUMO. It represents the lowest unoccupied molecular orbital. The LUMO, for example, for carbon is this. So this is the LUMO for dicarbon. And then the HOMO will be the highest occupied molecular orbital, in which case for fluorine that's pi star 2p. Okay, and then the HOMO, for example, for dicarbon is just pi 2p. Okay, we will work on this problem in class.